In this video, we'll talk about limits. In Calculus 1, we spend a great deal of time talking about limits, going over limit definitions, how to read a limit, and what they mean when we're evaluating or analyzing the properties of a function or a graph. Limits help us describe the function and see how it behaves as it gets close to any particular value or particular limit. We read limits like, if I'm looking at the example to the right, we read limits as the limit of f of x as x approaches 3. So it literally goes like that, the limit of f of x as x approaches 3. We let this function be defined on this interval, obviously, because we're seeing how it approaches that number or that value. The goal here is to see what the function does as it gets exceedingly close to the value, the x value, in this case 3. So exceedingly close to 3 without actually setting the x value as 3. This is like an important concept because we're approaching the value 3. We're not actually touching the value 3. And if you understand that concept, then you'll be able to understand most of all of limits. So right away, let's just get into some examples, and I'm sure this will start to make sense. If we're again asked to graph the limit of f of x as x approaches 3, we're told that f of x is this function here, x plus 2. So it's just a linear graph boosted up 2 points. So we have this function, or we have graphed this to the right here, just a 1-to-1 graph boosted up 2. All right. We're looking at the x value 3, and we're looking for the limit of f of x as x approaches 3. So the limit of f of x, meaning like we're looking for the y value when x is 3 for this graph. So to do that, we have to see what the graph does when we approach it from the left and the right hand side. If I'm approaching x equals 3 from the left hand side, I see that the y value it's going towards is y is at 5. If I approach the graph from the right hand side, I also see the y value that it approaches at x equals 3 is 5. Therefore, we say that the limit of f of x when x is approaching 3 is equal to 5. And we know that the value of f of 3 is equal to 5. This does not always happen. So make sure that even though that this is the case where these are both the same, they might not always be the same. And you're going to see some examples of that soon. Pretty straightforward. All right. Looks like getting pretty comfortable with this. So let's move on to another example. Oh, actually, let's talk about the other method on the theory behind taking a limit. So as I was mentioning earlier, when we're evaluating a limit, this is something that when we approach the x value that we're given. So we're approaching when x equals 3, but we'll never actually come and touch 3. So if we're given a table of values rather than a graph to look at, the table of values would be like, this is the x value as it's approaching 3. See how it goes: 2.9, 2.99, 2.999. Then this is the y value when this is happening. And see, as it's getting larger and closer to 5, we see that on the left-hand side, because this is smaller than 3, we see on the left-hand side that this is still approaching 5. If we do the same thing on the right-hand side, doing 3.1, 3.01, 001, 0001, blah, 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 you will also get a value that looks like it's approaching the number 5, being 5.1, 5.01, 5.01, etc. So that's the numerical analysis method of evaluating a limit. Now let's look at a slightly more complicated question. We're looking at the limit as x approaches 3 for g of x. G of x is defined by this piecewise function right here. tells us that g of x is x plus 2 everywhere where x does not equal 3. So basically, it's the same linear graph boosted up to, except that at x equals 3, we have an undefined value, meaning we have a hole. So if I was asking, between 1 and 7, if this function satisfied the intermediate value or the mean value theorem or Rolle's theorem, we would see that, like, even though this could be considered a continuous or a non-continuous function, or sorry, actually, you could be considered a continuous function, it's not differentiable across the whole interval because of this hole. You'll see the nuance onto why this is continuous but not differentiable. It actually comes from the fact that it has a limit here. So if I'm evaluating the limit at x equals 3 of both sides, I see that the value from the left-hand side and the right-hand side still approach 5. So we say here that the limit of g of x at x equals 3 is still equal to 5. However, the difference here is that at g 3 is an undefined value. So this is not something that we can take a derivative of. This is a non-differentiable point. However, it's still continuous because the values that there's still a value 5 there's still a limit there. If the limit is still being able to be taken, then you have a continuous function. It's just not differentiable. Limit exists, therefore continuous. All right, let's see. This is just kind of expressing what we were doing. We're looking for the limit to be true. And if the limit's to be true, it has to have the same value on both the left and right hand sides when we approach the x coordinate. If they approach the same y value, then the limit exists. If it does not approach the same y value, then the limit does not exist. Because we approach the value from the left-hand side denoted by this little minus sign and the right-hand side denoted by this little positive sign, and saw that they both equaled 3. Therefore, in our last example, the limit existed. So then, obviously, there's not going to be a time where a limit always exists forever and ever. There's going to be some limit discontinuities where now it's not a continuous function and our limits are not the same and don't exist at certain point values. Basically, as you can figure out, the limit discontinuity occurs when the following doesn't occur, when the limit doesn't exist. Whenever there is a time when you're approaching a value from the left and right hand side and they don't match the same y value, and this is just kind of like a rule of thumb thing right down here. Whenever you're like tracing the graph, if you ever have to lift your pencil while you're tracing the graph, then there's usually a discontinuity there that makes a break, so that causes a limit not to exist. Again, I think it'll be easier if we just look at some examples. In this example, we have f of x is equal to x squared because we have a simple parabola. They also tell us that. And we're asked to find what the limit of f of x is when x approaches 3. If we approach, this is x is 3 right here. If we approach f of x equals 3 at x equals 3 from the left-hand side, I see that it's about to reach the value 9. If I approach from the right-hand side, I also see that it's about to hit the value 9. So therefore, the limit of f of x when x approaches 3 is equal to 9. However, because of this hole here and this point specified down here, whenever we're asked what f of 3 is equal to, we actually need to specify that f of 3 is equal to this point down here, which is equal to 4. So whenever there's a hole or a point that's being specified outside of the graph, the exact y value when you're asked to put it down is whatever that point is. So it's not what the limit is up here. The y value at f of 3 is equal to 4, but the limit as the limit of f of 3 when x approaches 3 is equal to 9. So little things like that are important to keep in mind when you're asked to evaluate limits, whether it's continuous, discontinuous, or which have you. So we say that the limit exists, but since there is a hole here with a specified point, we have a discontinuity. Okay. In this example, we have two separate graphs, part of this function. This type of discontinuity is called a jump discontinuity. When the left side of the graph doesn't meet the right hand side of the graph. So if I'm approaching the function from the left, I'm up here and I'm thinking that the functional y value at x equals 2 is equal to 4 because I'm up here. However, if I'm approaching the graph on the right-hand side, I'm thinking that the right-hand side, or the limit when I approach 2 from the right-hand side, is equal to something like 2, or like, as we see over here, is like 2 root 2. So since the limit doesn't match each other from the left and right-hand side, the limit actually does not exist here for this graph or this function. Now remember, the rule is that this is only continuous at x equals c, or like x equals 2 in this, for our case, if and only if there is a limit that exists at x when it approaches 2. And since it doesn't exist, we have another discontinuity here. One of the most important discontinuities to be able to realize is when there's asymptotic discontinuity. Asymptotic behavior occurs very often in math and in real life science. So out of all of the graphs, I think this one is the most important to really be able to work with. Asymptotes are when the graph cannot be drawn without picking up. Like, so asymptotes are basically infinite barriers extending within the graphical space of your function where your function cannot cross. It's basically like an unbounded boundary, if that makes any sense. Like the distance it goes is unbounded, and it's a boundary that this function can never cross. So for instance, right here, we have a vertical asymptote where this function can get as close as it wants to that value, but it will never, ever cross the dashed line. It won't ever cross the plane, like theoretically speaking. And although since it gives us an infinite behavior, that doesn't actually mean that the limit has to exist or not exist. So you'll see that in a second when we do some examples. So let's just ask the question here: what's the limit of the function at x equals 2? So if I approach 2 from the left-hand side, I see that the graph is going towards negative infinity. So I say that this is negative infinity. If I approach 2 from the right-hand side, I see that this is going towards positive infinity. Therefore, this would be positive infinity. These two limits don't match each other from the left and right-hand side. Therefore, the limit at x equals 2 does not exist. However, as you'll see in a coming example, that does not always happen. So the uses of infinite limits can be used to approach these values for an infinitely increasing or decreasing functional y and y value, which, as I mentioned before, happens very often in math and science. And the thing that I was hinting at before is that for a limit to be true, they just have to be the same evaluation from the left and right hand side. So it doesn't matter whether it's infinite or not. The limit can still exist even if there is an asymptote with infinite behavior. And we can see that with this example here. So if I'm asking what the limit is, if I'm approaching x equals 0, if I'm approaching from the left-hand side, I think that the limit of the graph approaches positive infinity from the left-hand side. It also approaches positive infinity if I look at it from the right-hand side. So therefore, I would actually say that the limit here does exist at x as x approaches 0, and that the limit is infinity because the limit on the left and right-hand side are the same or equal. So just because it has an infinite behavior or asymptotic behavior, that doesn't mean that a limit won't exist. Even though that this isn't like a continuous function, like there's literally nothing we can do at this point. The limit here exists and can be evaluated. So it's just something to be very aware of when dealing with these. Let's test ourselves with one more example, or maybe two more examples. In this example, we're tasked to find the limit as x approaches 0 for 1 over x. 1 over x is a very standard graph that will happen and show up a lot, and you'll be familiar with. It looks like this. So if I'm asked, what am I asked? I'm asked to see what the limit is as x approaches 0. So right here at the origin. So I'm looking to see what the graph does on the left and right hand side. On the left hand side, the function approaches a negative y value, infinitely negative y value. So I'll say that this is approaching negative infinity. On the right hand side, the graph is approaching an infinitely positive y value. So I'll say that on the right hand side, it's approaching positive infinity. Because the left-hand side and right-hand side do not equal each other, the limit here does not exist because the left-hand limit and the right-hand limit are not equal. Hopefully, you're starting to get comfortable and a good understanding of how these limits are how we evaluate properties of graphs using limits. All right, one more example. The limit of f of x as x approaches positive infinity. So this, again, you can also ask when x approaches infinite values. So instead of asking when what the graph is doing at a particular x value, you can ask what the graph does when the graph goes to an infinite x value or a negatively infinite x value. So if I'm given a graph that looks like this and I'm asked to figure out what the function does when x approaches infinity. So x approaches infinity going this way and that way. When x approaches positive infinity, I see that the function is going towards a y value of 2. And if it at negative infinity, I see that it's going towards a y value of 2. So you can't really approach infinity from the left and right hand side. So when you're asked about like abstract x values, you really just check and see what's happening on positive and negative infinity. For both positive and negative infinity in the x direction, you see that the y value is at y equals 2. So because of that, the limit to the left and the limit to the right are actually equal, and the limit here exists. And we said that the limit is equal to 2. So there we've gone over all of the limit discontinuities and how to evaluate and read graphs using limits. Importantly, you should just remember that if the limit only exists if it's the same y value approached from the left and the right hand side of whatever is being asked. And then once you've been familiar with that, then you'll be comfortable whenever you see jumps or asymptotes or gaps. Whenever you'll see that, you'll know that there'll be a limit or no limit. And if you can use these important theorems that were discussed earlier, because all of these is really to just check and see if you have a differentiable or a continuous function, and that if you can take the derivative of it and whatnot. So very important to get comfortable with.